Could a single impact have briefly turned Umbriel into a cryovolcanic world? We'll learn more this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Today we're going to explore one of the most overlooked moons in the outer solar system, Umbriel. It's a dark and heavily cratered satellite of Uranus that's long been considered geologically dead. But a bright ring inside one massive impact crater may tell a very different story. My guest is Adeene Denton, NASA postdoctoral program fellow at the Southwest Research Institute and lead author on a new study in the Journal of Geophysical Research, Planets. Her team takes a closer look at the Wunda impact crater on Umbriel and asks whether this ancient collision briefly awakened a dormant moon, triggering cryovolcanic activity from beneath its ice shell. Then in What's Up, I'll join Bruce Betts, our chief scientist at the Planetary Society, to talk about one of the key physical mechanisms that can keep ocean worlds from freezing solid, tidal heating that's driven by orbital resonance. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we take a mental trip to the outer solar system, I have a quick note. Our spring membership drive is happening right now. We're working to welcome 250 new members to the Planetary Society, people who believe space science is worth fighting for. Memberships start at just $4 a month, and it helps power everything we do here at the Planetary Society, from our advocacy work that helps save NASA science to Planetary Radio. If you'd like to stand with us in support of the scientific exploration of space, you can join today at planetary.org. Now let's flash back 40 years. When Voyager 2 flew past Uranus in 1986, it gave us our first and only close-up look at Umbriel. And what we saw looked pretty bleak. Umbriel is the darkest of Uranus's major moons. Its surface is battered with craters, and it doesn't have the dramatic canyons of Ariel or the chaotic terrain of Miranda, some of the other moons of Uranus. So for decades, it's been treated as a control sample, the quote-unquote boring moon in the system. But there's one feature on Umbriel that just doesn't quite fit that narrative. Near Umbriel's equator, there's a 131-kilometer wide impact crater called Wunda. Its crater floor contains a ring of bright material, which looks really out of place when you compare it to the moon's otherwise charcoal dark surface. So the question becomes, what is that shiny reflective material inside that crater, and how did it get there? Is it fresh impact material? Maybe some dry ice that got cold trapped in the crater? Or could it be something more intriguing? Salty deposits left behind by briny water that once reached the surface of this moon. That's the mystery at the heart of a new paper published this year in the Journal of Geophysical Research, Planets. It's called Assessing the Plausibility of Past Cryovolcanism on Umbriel Using the Wunda Impact Crater. Dr. Adeene Denton, who's a NASA postdoctoral program fellow at the Southwest Research Institute, is the lead author on this paper. She and her colleagues used shock physics simulations to reconstruct the colossal collision that formed Wunda. By matching the crater's shape and the structure, they work backwards to infer what Umbriel's interior must have been like at the time of the impact. And if Adeene's name sounds familiar to some of our listeners, that's because she's joined us twice in the past to talk about smashing worlds together. She helped model the possible kiss and capture of Pluto's largest moon, Charon, and explored the origins of Pluto's famous heart-shaped region. Her specialty is using high-powered simulations to recreate catastrophic events in the history of icy bodies in our solar system. And now she's turning that expertise toward Umbriel and the Uranian moons. The geometry of Wunda crater holds clues about the moon's thermal state billions of years ago. And if that ice was warm enough, even temporarily, the impact that formed Wunda may have created the situation necessary to produce cryovolcanism, icy eruptions from beneath the crust. And yes, we're drawing big conclusions from 40-year-old images of a single impact crater on a distant moon of Uranus, but this is about more than one crater. It's about what makes icy worlds active in the first place, what conditions allow for cryovolcanism to happen, and it's about liquid water. not a permanent ocean, but something dynamic and temporary. Because where liquid water exists, even if it's fleeting, we can begin to get a better picture of where there are conditions in our solar system and beyond that could be habitable, and how these icy moons and their oceans change over time. Here's my conversation with Adeene Denton. Hey, Adeene, welcome back.
It's great to be back.
Well, so you've told us over the last year about all these wonderful things about Pluto and Charon/Karen, depending on how you want to pronounce it. But we're back with some more icy bodies. I remember you spoke a little bit about it last time, but how did you get into researching Umbriel specifically?
Well, I'm very excited about the potential for NASA's next flagship mission to be a Uranus orbiter probe mission. And I'm really hoping to be on kind of the ground floor of helping with designing science objectives for that mission. Obviously, the Uranus orbiter probe mission would take at least 30 years. So the role of scientists now is to revisit everything we learned from Voyager 2 and think about how we can plan the next mission so that we build on the knowledge that we already have and learn as much new stuff as possible. So I've been working with some folks at the Jet Propulsion Laboratory and elsewhere, thinking about how, of the 5 main moons of Uranus, what we can learn about each of those when we return. And Umbriel is a really interesting and unusual case because the imagery is kind of not good. If you Google Umbriel and you look at pictures of it, you'll see the one picture that we actually have 6 total, but there's one good one. So it's a little bit tough, but there's actually a lot that we can learn from that one image. So it turned out to be kind of an interesting challenge to try to dig into what we think is going on underneath based on the little information we have.
It's interesting because just a few weeks ago, I was speaking with Linda Spilker, the project scientist for Voyager, and it was literally, I think, like a month to the day before that flyby anniversary, the 40th anniversary, which was on January 24th, right? So it's been 40 years since we flew by this body, and we only have limited understanding of what's going on there, and yet we're still finding new ways to piece together the mysteries about this world. But I think what's really interesting about it is that for decades, Umbriel was basically treated as this kind of dull baseline in the Uranian system. Like, why did planetary scientists come to see Umbriel as this basically geologically dead moon compared to things like Ariel or Miranda?
This is so insulting because the most boring moon is Oberon and not Umbriel. So everybody out there, get your facts straight. It is worth being said, for anybody who's not thinking about the Uranian system as much as I am, which is fair, the 5 major moons of Uranus are in increasing distance from Uranus: Miranda, the tiny one that's incredibly geologically active, then Ariel, which is also very geologically active, Umbriel, then Titania, then Oberon. So of those, Miranda is the small, really neat one that has all these really weird geologic features on it, and Ariel has these massive canyons, but there's also kind of a imaging bias here because the best resolution of images that we have are also of Ariel and Miranda. So part of the reason why they may seem more geologically active is simply because we can literally see more when we look at their surfaces. That being said, Umbriel is the sister moon of Ariel, and we call them sister moons because they are very similar in size in addition to having similar names. Umbriel has an incredibly dark surface, and it appears to be very heavily cratered. And usually from a geology perspective, when you see a moon that is mostly covered in craters, that is often a sign that not much is happening. And the reason for that is what geologic activity does is renew a planetary surface. So say on an icy moon, you can have cryovolcanism that erupts, covers the surface, and then buries existing craters. So the more active you are, the more likely you are to kind of overprint craters. Whereas if you're not very geologically active, you can just kind of hang out for 4 billion years and just accumulate craters forever. So Umbriel didn't have a very promising start when we looked at the one good photo and the 6 total photos and saw mostly craters. We don't necessarily have a complete handle on what we call the population of impactors that hits Umbriel. It's all kind of a guess. This is going to be a longer explanation of how we do age dating of surfaces in the outer solar system. It's a little bit tough. Basically, on any body that isn't the Earth or the moon, where we have samples to kind of ground truth the ages of the surface, we are guessing at how old any given surface is. What that means in practice is we have 2 kinds of ages. and they're both relative. The first is you can look at a surface and say, look, this part of it has more craters than this other part. So it's older because it's been around long enough to accumulate more craters and get hit by more stuff. That is fundamentally what crater age dating is. So if you then compare Ariel to Umbriel, and you can tell that Ariel has less craters than Umbriel, that would potentially indicate that Ariel's surface is younger than Umbriel, but not how much younger or how old either of them are, right? So it's a relative distinction. It could have been that Umbriel was very geologically active at some point and then stopped and then started accumulating craters after that. The same way we think that Venus potentially had kind of a global, almost kind of all at the same time, series of volcanic eruptions that reset the age of the surface. That could have happened. It also could not have happened. The other component of age dating is understanding the likelihood of things hitting Umbriel based on its position in the solar system. So when we age date anything in the solar system, we have to say, okay, what is the frequency of stuff hitting any of these bodies through time? And that is, again, an estimate that you have to make based on what's nearby. So in the outer solar system, that's going to be comets. So that you can estimate like the comet flux coming into the Uranian system through time. And then that can allow you to build your age of any of these surfaces. But you can see how that would be kind of difficult to do, right? Because we don't actually know if the flux changed through time or not. And moreover, in the Uranian system particularly, it's highly likely that something happened because Uranus is on its side and the whole system is on its side. And one of the most likely ways to do that is if a really big body, like super Earth size, comes in and hits Uranus and tips it over. And that if Uranus already had a satellite system, likely disrupt that system, and then all of those moons have to reaccrete, and then you get Umbriel as it is today. So there's a lot of kind of uncertainties when we think of how old a surface is and whether that means a body truly has been geologically inactive since it formed.
This world basically is just super dark on the surface, clearly undisturbed. It's basically like a charcoal brick that's been floating through the void for a while. And then there's this one feature that really, really stands out. So is it Wunda or Wunda crater?
I'm not sure.
I've always called it Wunda, so I'm just going to go with Wunda.
I say Wunda.
All right.
I say Wunda. We'll be saying Wunda on this podcast.
Yeah. So why has Wunda crater been something that's really puzzled people ever since Voyager first imaged it?
Well, it's the only thing on the surface that isn't super dark. It's not just that it's not super dark, it's extremely bright. And it also looks like it's at Umbriel's North Pole. So if you look at a picture of Umbriel, right at the top, there is this crater that is full of this really bright white material. Of course, this is the Uranian system, so that means it's actually at the equator because Umbriel is tipped on its side. But really cool.
That is really cool.
Yeah. And it's really strange because how do you get really bright material on the surface of an icy moon? There's two ways you could do it. Either something comes in and hits Umbriel and then just kind of dumps that off right there, or it came from within Umbriel and erupted onto the surface through a form of cryovolcanism.
Before you did this work, what was the leading hypothesis, or what were the leading hypotheses for where all this bright material came from?
Those pretty much are the two leading hypotheses. Either the material is endogenic, so it comes from within Umbriel, and the way you would do that is if you had a form of cryovolcanism. So cryovolcanism meaning volcanism, but it's ice. So unlike with Enceladus, where cryovolcanism means jets coming out of the South Pole, the theory here would be that you have cryovolcanism that's produced from the impact itself. So when a comet comes in, hits Umbriel to make the crater, it can potentially enable material from beneath the surface of Umbriel to then rise to the surface through the fractures that are generated by the impact. In some cases, produce the melt as well, that then erupts onto the surface and fills the crater floor. And that is the bright material. The other alternative is that it's not from inside Umbriel at all, and it's instead a surface deposit that formed in the crater, potentially long after the crater formed. In that case, you could have delivered it by comets, or it could have just condensed from elsewhere on Umbriel's surface.
So it's either probably some kind of like dry ice, CO2 kind of thing that we see in a lot of craters, or it's something more like what happened with Ceres and those bright spots that we've seen in the past, right? What kind of material would be on the surface that would allow for that much reflectivity?
It depends. So one of the things that we noticed upon looking at Wunda was the potential connection to Akator crater on Ceres. And the paper that I published here has a companion paper where we talk about that in more detail. But basically, Akator crater on Ceres has these bright deposits. We call them faculae on Ceres. We do not have such a name for the bright deposits inside Wunda because we know so much less about them. In that case, on Ceres, they're made of salts. So they're salt deposits. On Wunda and on Umbriel, it's a lot less clear just because we don't have that kind of specific compositional information. We have bulk information about the surface of Umbriel and some recent from telescopic observations. But because of that, you're getting a sense of what the bulk surface of Umbriel is like rather than the material inside Wunda. But yes, it's likely some form of volatile ices, potentially salts. It depends on what it is. If it's condensed material, it could be condensed CO2 ice. But either way, it's some form of volatile material.
You mentioned this earlier, that it appears as kind of like a ring shape where that crater is. What does that tell us about the actual topography of this crater?
It tells us a couple things. The ring indicates that the bright material is probably embaying a central peak in the center of the crater. From a cratering perspective, what that means is, as a fairly large crater, what happened when Wunda formed is that a comet hit the surface of Umbriel, excavated the initial crater, and then when craters get large enough, they excavate so deep that when they excavate, they kind of oversteepen and collapse to form complex craters which have central peaks in their interior. So when we think of impact craters, normally we just kind of think of like a bowl shape, but as you grow in size, crater morphology gets more complex because of the way crater excavation interacts with the subsurface of a planetary body. So in this case, it seems like Wunda is a complex crater that forms this central peak.
Well, obviously, we can't drill into Umbriel to learn more about what's going on beneath the surface. So in classic Adeene fashion, you modeled this. I gotta say, every time I talk to you, I love hearing about what new things you're smashing into other simulated things. But in this case, you're trying to kind of like work backward to see what this crater can tell you about the interior of this world. How does that crater shape act as a diagnostic tool to tell us what's actually happening underneath the surface?
Crater morphologies are the progression from a simple to complex crater is something that we see on basically every planetary surface. But the transition from simple to complex and how you get a complex crater is dictated by what's going on beneath the surface of a planetary body. And I'm going to use the moon for an example because the moon has so many great craters. You can look at craters of the moon all day and you'll see great examples of all kinds of craters. The reason why you get a complex crater on the moon is because as you excavate the crater, and I'm making a big bowl shape with my hands because everybody who does cratering loves to do and here comes the big hole in the ground. The inward collapse is driven by gravity, but it's also driven by the fact that the moon, like the Earth, has a crust, and underneath that it has a mantle. And those distinctions are somewhat compositional, right? The crust is made of a different material than the mantle, but they're also rheologic. And what I mean by rheologic is they deform differently. So the crust is cold, close to the surface, and kind of brittle. The mantle, being deeper, in addition to being a different composition, is warmer and flows more readily. So what happens on the moon is you excavate deep enough to mobilize the mantle. So when you have an inward collapse, the mantle flows inward. And because it flows more readily, is warm and weak, flows inward and helps create a central peak. The question then becomes, on an icy body, you don't have a kind of crust mantle distinction, right? We have ice, and then if we're lucky, underneath the ice, we have ocean. That's a little bit different. When it comes to understanding why and how we get a transition from a simple to a complex crater on a body like Umbriel, it raises questions about what Umbriel's ice shell is actually like, what it's made out of, and how it behaves.
What tool did you actually use to do this modeling?
I use 2D impact models for this. I use the ICEL 2D shock physics code, which is... How much do you want me to explain about it?
You already said the most important thing, which is that it was flat, but go to GitHub.
I'm going to try to explain this in a way that's like interesting, but I mean, it's codes. I used one of the major shock physics codes that impact modelers use. It's called ICEL. And I used the 2D version where we just simulate Umbriel as a flat plane. The reason why I can simulate Umbriel as a flat plane is not just because it's easier to do, but that's true, it is, but because Wunda is not very big. So when I simulate Pluto, and when I simulate Charon and Pluto smashing into each other, that mobilizes the entire planetary body. So you need to do it in 3D, and you need to be thinking about how the whole body is going to respond. Wunda is only around 125 kilometers across, which is a small fraction of the total radius of Umbriel. So the curvature of the planet doesn't really matter. What we're interested in is what's going on in the immediate vicinity of the crater. So we just simulate Umbriel as a layer of ice, which we're then exploring what's going on inside the ice layer. And then depending on at what point we're looking at in terms of Umbriel's thermal history through time, we also add in an ocean layer before we get to the rocky core. Because even though Umbriel looks the way it does now, it's highly possible that at least at the beginning of its history, it had an ocean, which then slowly froze through time. And we know that mostly from thermal models.
Well, right out the gate, you would think that it would be the impactor itself that would really matter as the variable, right? But in the paper, that object is essentially fixed. What kind of impactor did you simulate, and how was that choice itself constrained by what we see about this crater today?
Sure. Well, when we're thinking about what's hitting Umbriel, you do technically have a lot of options, but what we're actually constrained by is the size of the crater. There has been extensive study on how impact cratering works, and in particular, what the trade-offs are between the size and the speed of an impactor hitting a surface. What that means in practice is we have a good handle. We've developed scaling laws that allow us to think, okay, if you have a crater of this size on this body, what size impactor is going to hit it? And that means we can make a pretty good guess as to what size of body it is. In the outer solar system, you can also make a pretty good guess as to what material it's made out of. Here we assume it's an ice ball, so likely a comet of some kind coming in and hitting Umbriel. The speed at which these things happen is also something that we develop scaling laws for this too, because there's no real way to know how fast something is going to hit something else, but you can make a pretty good guess at an average speed. And the way you can make a pretty good guess about the average speed is by thinking about what accelerates an impactor toward a body. So what that depends on is the gravity of the body in question, but also, if it's a moon, the gravity of the planet in question that it's orbiting around. So I'm going to use Mercury for this. Mercury is orbiting really close to the sun. What that means is anything that makes a crater on Mercury is actually driven a lot by the gravity of the sun. It's basically going towards the sun and then missing at the last second and hitting Mercury. What that means in practice is things that are hitting Mercury extremely fast. The average impactor speed at Mercury of something hitting Mercury is between 30 to 50 kilometers per second.
Yikes.
That's crazy. It's not good on Mercury. It's really tough.
Poor Mercury.
But if you go all the way back out to Pluto, Pluto is so far away from the sun. It's not orbiting anything other than the sun. It's just out there by itself. Well, and Charon is also there. But Charon's not big enough to divert anything that's going to hit Pluto. Something that's hitting Pluto is hitting Pluto at around 2 kilometers per second. So an order of magnitude decrease in speed. And that's just because there's nothing else to accelerate a comet towards Pluto except Pluto. So it's a very gentle kiss. When you think about Umbriel, which is a small moon of Uranus, a small giant planet, you end up with an impactor speed that's somewhere in the middle.
So if the impactor itself isn't the most important question here, then what moon parameters did you vary in the models?
The internal structure of Umbriel, which you can gather from this discussion, is a guess. We're making educated guesses about the Uranus system. We can be pretty sure that Umbriel is ice and rock. What we can't be pretty sure of is what that ice has done through time. A lot of the way we try to figure that out is through thermal modeling, where we think about, okay, based on Umbriel's size and estimates of its density, It probably formed with some amount of ice and some amount of rock, and then that rock made its way to the inside to form a rocky core, and then the ice made its way to the outside to form the ice shell. But from that, how do you get from forming the moon to the present day? So there's a lot of people that do thermal models to try to look at that. And within all of those thermal models, it suggests that you form Umbriel early on, and it's kind of hot at the start because a lot of moons and planets are hot at the start from the heat of accretion. And then it slowly cools off through time. And as it cools off through time, if it has an ocean, that ocean becomes a small relict ocean, this thin kind of strip beneath a thick, cold ice shell. That's at least what the traditional thermal models tell us. And they're traditional models because they just assume Umbriel forms and then nothing happens to it other than cooling off through time. If that's the case, then you end up with a cold moon that's not doing anything today.
So what if we had like the simplest case possible here and Umbriel was literally just a cold, thick, rigid block of ice? What happens in that scenario?
Well, the problem is, if that was the case, the impact model suggests that you can't form a Wunda-like crater. So we were a little bit at a loss. Basically, what happens is if Umbriel is as cold as it's predicted to be today, the surface temperature at Umbriel is 55 Kelvin. So it's a little cold.
Just a tad bit.
Just a tad cold. And then if it stays cold throughout most of the ice shell, as it's predicted to do, then that ice shell is so cold and so hard that it effectively behaves like rock. And what that means in practice is you excavate a really big, really deep hole, which doesn't seem to be what Wunda actually looks like today. And the main reason we think that is because the bright deposits seem to embay that central peak. So if Wunda has a central peak, it cannot be a big hole with no central peak. But we now have two pieces of geologic evidence that are seemingly contradictory. We have thermal models which tell us Umbriel should start out kind of warm and then get cold. And then we have a crater that seems to suggest that Umbriel must have at some point been warm enough that it could deform enough to have inward collapse in the production of a complex crater with a central peak.
What about the other extreme? What if we say that it's a thin ice shell? You might be able to produce the right crater size, but there's still some physical problems there.
Well, the main physical problem is it's very difficult to keep a thin ice shell around long enough to accumulate craters. So if the ice shell is super, super thin, you can punch all the way through the ice shell and expose the ocean. Clearly not what happened here, because again, if you fully expose the ocean to space, there is no central peak. But the biggest problem with having a really thin ice shell and a really thick ocean is that it's just not favorable. We don't think that's what happened. And it then places the formation of Wunda really early on in Umbriel's history, because the only time you could have a really thin ice shell and a really thick ocean is if you form Wunda specifically right at the start of Umbriel's geologic evolution, which is possible but convenient.
That's true. I mean, it's clearly an old crater, but even then you have to figure out how the material underneath turned into a cryovolcano in a circumstance where the whole thing cooled already a long time ago. There's
a lot of problems, yeah.
Yeah. So this leads you in the paper to what you call the warm sandwich model, which classic space terminology, it's always either some kind of food or Lord of the Rings or the shape of something. But so we've got a warm sandwich. Can you explain what that structure would look like inside of Umbriel?
I will have you know that the terrestrial geologists are also doing this, okay? We have different models for the Earth's crust, and they're called creme brulee, jelly sandwich, and banana split. So please don't let geologists off the hook either.
Science in general. We're all hungry.
We are so hungry all the time. Yeah, the warm sandwich model is our attempted solution because, yeah, the easiest way to make Wunda would be if you have a thin ice shell and a thick ocean, but that's not very geologically favorable. So then the alternative has to be you have a thicker ice shell. Umbriel's ice shell today is likely over 100 kilometers thick, close to 200 kilometers thick, really, really thick ice shell. If that's the case, then you need to weaken the bottom portion of the ice shell such that you can kind of mimic the crust mantle dynamic that we have on terrestrial bodies like the Earth, the Moon, and Mars. If Umbriel has this kind of warm, deforming layer, then it's no problem. You can make Wunda quite easily. And if that's the case, then if we think about what makes the bright deposits in its interior in that scenario, the other thing that happens when you form a crater is you deposit a lot of heat under the crater floor. The reason for that is, of course, because you're transforming the kinetic energy of the impact into thermal energy as everything deforms. So everything around the crater gets really warm, and you can concentrate a melt chamber underneath the crater floor, which could then theoretically, as the chamber cools over time, get pressurized and erupt to produce the bright deposits.
So it's possible there isn't a liquid water ocean under there. There just happens to be a melt chamber caused by this impact?
It could be the case. This is also what we think happened on Ceres for Akator, or at least one of the theories to produce the faculae or the bright deposits on the crater floor of Akator is you create the crater, and then a couple things happen kind of simultaneously. The first thing that happens is you excavate the crater floor, and then as the crater collapses, you produce an impact melt chamber underneath the crater floor, but then you also fracture and damage the ice shell close to the surface. And again, that's just kind of a natural response to impact. If we've noticed in terrestrial craters that you end up with these widespread fracture zones associated with the crater floor. And on the Earth, it's been suggested that those could potentially be really useful hydrothermal systems, potentially for the evolution of life. On Umbriel and on Akator for Ceres, those fractures can then provide the networks that allow melts from a melt chamber to reach the surface.
The problem, though, is that apparently this crater is really, really old. So if we suppose that this melt chamber was created back when that impact happened, who knows how long ago that was, but the material deposited on the surface, if it's some kind of salt, right? When we're thinking about the information we got from Ceres and Dawn, it suggested that the material deposited on the surface would darken over the course of maybe 10 million years or that time scale. So how do we get from this impact happened a long time ago, created a melt chamber, to we have a more recent, probably in the last 10 million years, deposition of cryovolcanic material on the surface? Like, what creates that time delay?
There's a couple options. So yes, one of the issues with bright deposits is, and the reason we don't see them so often is because they tend to be pretty young. And the reason why bright deposits like Akator faculae or the bright deposits on Umbriel might go away is because, again, all of these bodies are constantly getting bombarded by material. And that tends to destroy bright material, and you end up with a darker surface over time. So yes, it's highly likely that space weathering would remove the bright deposits if they are relatively old. So there are two options. One is that Wunda is indeed old. And if that's the case, then the bright deposits likely post-date Wunda by a significant amount of time. And if that's the case, then they probably are exogenic. They probably are delivered from somewhere else, and they've reached Wunda long after the crater formed. But the alternative is that Wunda is young. Or if not, 10 million years young, because that would be incredibly young. I would never say that. That would be a big crater to be that young. But say Wunda formed in the last billion years. That would still be a relatively young crater. If that's the case, then potentially you can wind up with a long-lived impact melt chamber that then erupts in the ensuing tens of thousands to millions of years after the crater formed. And you end up with a somewhat long-lived bright deposit. The problem is we just don't know enough Umbriel to actually be able to answer these questions and resolve these uncertainties.
We'll be right back with the rest of my interview with Adeene Denton after the short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, The Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
If we go back to that idea of, probably what is the most likely scenario here, which is that you've got this warm sandwich, right? You have the really cold, icy layer. You have a slightly warmer, icy layer underneath, and then everything going on underneath that. You're going to need some kind of energy source to keep that a little warmer than the rest of the ice, right?
Yep.
I mean, there are a few ways that you can do this, right? Clearly, you have a bunch of bodies out there in the outer solar system that still have liquid water oceans, despite being nowhere near the sun. And one of the options you could have is, say, radioactive material, radioactive decay. We know that half of the internal heat of our planet, as an example, is from that radioactivity. But you still don't think that's the case with Umbriel. Why is that?
No. And the reason for that is because we have pretty good thermal models at this point that rely on the main source of heat for that being radiogenic decay. So once Umbriel forms, then if its only heat source is radiogenic decay of isotopes in its rocky core, then it doesn't warm up very much at all. And the ice shell likely stays really cold the whole way through and thus doesn't really get weak at all. The other heat source that you would need if we're going to heat up the ice shell, and that's potentially not the only option for how to do this, it's just the most likely one and the easiest to explain, is if Umbriel passes through a resonance with some of the other Uranian moons. This is a situation kind of like the Saturnian system. So in the Saturn system, we have all of these really nice mid-sized moons. Mimas, then Enceladus, which is the geysers one, great moon. Tethys, Dione, Rhea, Titan, and Iapetus. They're all kind of comparable in size. Obviously, Titan is the really big guy. And because there's so many of them that are comparable in size, they pass in and out of resonances with each other, which means their orbits around Saturn will kind of line up such that they're in kind of the same place at the same time in their orbits. And what that does is it produces additional heating inside each of those moons. If they're passing through a resonance, then they're not just experiencing tidal heating from Saturn, they're also responding to the other moon when they're lined up with each other. This can also happen in the Uranian system because, again, there are 5 moons that are kind of comparable in size. The problem is, like with the Saturnian system, it's hard to know when a resonance can happen. We just know that they can, and how long they happen for, because the duration of a resonance will then tell you how much additional heat you're going to get. And it becomes a very difficult and non-unique problem. So the easiest way to get additional heat for Umbriel is if it ends up in a resonance with one of the other Uranian moons.
But my current understanding is that the moon is not presently in a resonance that we know of. Is that right?
Nope.
So
no, it is not.
This is just one more example of why the whole Uranian system is so weird, because there, if that was the case, it happened quite a while ago, and then insert thing here happened, and now it's no longer the case. So what does that tell us about the history of not just Umbriel, but potentially the entire system?
Well, how many times can I say there are a couple options in this recording? I could say it a lot of times. There are a couple options for this. So we don't know the age of the Uranian satellites relative to Uranus because we think that something came in and hit Uranus and tipped it on its sides and then potentially completely reset all of the satellites, including how many satellites there even were. Once you then reset the system, we're now tipped on our sides, then all of the satellites are kind of in their current positions, but that doesn't mean that they get stuck in a resonance and stay there forever. In the Galilean system, those moons are so lucky that Io, Europa, and Ganymede are all in these nice resonances with each other. But in the Saturn system and the Uranian system, because there are so many moons that are similar in size to each other, they can fall into and out of resonances through time. What that means is you can have a spike in heating long after a moon formed, but then also have that heat source go away later. That's what makes things so difficult when it comes to understanding the lifetime of ocean worlds for both Saturn and Uranus, because you could form oceans and then have those oceans slowly decay. And we won't know the lifespan of the ocean unless we can better track the surface geology to see how the surface geology has responded to the growth of an ocean underneath an ice shell. So it's kind of a tough but really interesting question when we're thinking about ocean worlds, because I think a lot of us think of Jupiter's moon Europa. It has an ocean. The ocean is probably old. It's been there for some amount of time. But for Umbriel or some of the other Uranian satellites, if they've had oceans, or if they still have them today, those oceans might not be all that old.
We were talking about this fairly recently on an episode about Europa's potentially quiet seafloor, right? Even though it still has a liquid water ocean, there's a high chance that there's no actual hydrothermal activity or like faulting on the seafloor, even though there was in the past. So in each of these scenarios, whether it was habitable, whether it was not, whether there's water now, all of these situations at some point come to an end. So it introduces this interesting idea of like a dormant ocean world that once had this opportunity and is now totally different from what it used to be, which kind of reframes how I think about ocean worlds in general.
Yeah, I think we think of ocean worlds as being an ocean world as a static state that you enter, right? But that's probably not the case. What we're seeing all over the outer solar system is ocean worlds in different stages of their lifespan. And I think that's a really neat aspect of ocean worlds that we don't consider. So Enceladus and Europa are in their active stage. Saturn's satellite Mimas, which libration measurements suggest has an ocean, but its surface geology doesn't reflect that. It might be a young ocean, and the ocean is still growing, so we don't quite see it on the surface yet. And in the case of Umbriel, it may have been much warmer and been an ocean world in the past, but now that time has ended. It may not have ended, to be clear, but it was likely warm in the past and it may not be as warm now.
That's a cool idea, and one more reason why we have to go back to the Uranian system, because if we can take some kind of spectroscopic measurements, that would tell us whether or not this is in fact some kind of salts rather than some kind of CO2. And, knowing that and all the other systems we stopped to look at, that could give us some kind of idea of how many ocean worlds might be out there that we're not accounting for in other systems. These might be way more prevalent than we even thought they were.
Absolutely. Yeah, what we need from a Uranus orbiter probe mission, if it does do flybys of Umbriel, which would be extremely useful, is better images of Wunda, but also, spectroscopic information. We don't know what this material is, but we also currently don't really have a handle on its actual regional extent. And the reason for this is, if you look at a picture of Umbriel, again, you should do this. Everyone should look at a picture of Umbriel at least once. And you see Wunda and the bright deposits. One of the issues that we have when we think about how big those bright deposits actually are is the limitations of the ISS camera on Voyager 2. Because one of the things that's really difficult when you're really far away from the sun and you're already trying to take longer exposure images to be able to resolve things is that contrasts in brightness can wash out really easily. So you get these pixels that are super oversaturated with brightness in a way that we were able to take much better pictures of the bright deposits with dawn at Ceres, because imaging technology has improved quite a lot. So to be able to better characterize Wunda's bright deposits, we need better images of it so that we can actually see how big those bright deposits are and what they actually look like, and then also what they're made out of. And with those two things combined, I think we could answer this question.
Plus, there's a bunch of that moon that we haven't seen yet, right? We have just a fraction of it mapped. So who knows if there's some other cryovolcanism happening somewhere else on that world that we just don't know about.
There's a whole other side of Umbriel that we just haven't seen yet.
Yep. It could be one of those backside of the moon situations. They're so different from one another. It's terrifying.
That's what makes the outer solar system, and when I say outer solar system in this case, I mean the Uranian and Neptunian system, so interesting, is because we really do have just in some cases, half and less than half of a picture of the surfaces of these moons. There's so much that we're not seeing, and that'll help us really put the picture together for how the system formed.
Well, I think it's really amazing that you've been able to get this level of granularity with so little information. You only have a few images. You don't know what the composition is like. You don't really know what the internal structure is like. There's so much we don't know. And yet here we can have a totally valid conversation about what happened in the past of this world, whether or not that has some indication for habitability in the broader universe. I mean, I think that's really spectacular. We need to go back to that system and learn more, because this is just one moon out of all the other moons there. And Uranus itself is just such an enigma. I want to know more. So are there any other puzzles in the Uranian system that you would be intrigued to know more about?
There are so many puzzles in the Uranian system. I think the Uranian system is just fantastic because it's so unusual. Miranda, obviously, it is the coolest one. Everybody agrees that Miranda is the cool one, and they're right. Miranda has these features we literally do not see anywhere else in the solar system. They're called the coronae, and it's hard to describe. The coronae are these massive chevron-looking features that have these kind of tiered canyon cliff structures. One of these has the tallest cliff in the solar system. Verona Rupes is the tallest cliff in the solar system. It's 11 kilometers tall. And we don't understand how it got that cliff or any of the geologic features around it. We're not sure. One possible suggestion is that Miranda got blown up and it came back together, and that's why it looks like that.
Well, that might explain a lot.
But the alternative is that the ice inside Miranda is convecting in an unusual way that is forcing it to do that. And we just don't know. We really aren't sure. And again, we don't know what the other side of Miranda looks like, so it's unclear. Ariel, which is next to Miranda, may have had cryovolcanism, it may not have had cryovolcanism. It's really difficult to say, but studies of one of the craters on Ariel, the one we have the best picture of, suggest that Ariel also went through much higher heat fluxes than predicted. So it's possible that both Umbriel and Ariel went through phases in which they were a lot warmer than they are today. And that could then, in the case of Ariel, drive its potential cryovolcanism. So what's interesting about these moons is that things have clearly happened to them, but we don't know when and we don't know how.
Man, if I had a time machine, the weird space things I would go back in time to see, Uranus would definitely be in that list.
Ooh, I want to see the initial impact.
That impact would be really cool. Going to see what happened with Pluto and Charon would be cool. I want to see what happened with Venus. Why does it rotate like that? Who knows?
Ooh, don't worry about it.
Are there any other icy bodies that you're looking forward to learning more about in the future?
Right now, I'm really interested in the Saturn system because, again, there's so many moons there that they provide a really nice laboratory. And what they have over the Uranian system is just that we have better pictures and better data. I'm really interested in kind of following this question along of what is the lifespan of an ocean world? What does a young ocean world look like? And what does an old, extinct, relict ocean world look like? How can we identify those with limited information? I think that's really critical to understanding how the different satellite systems of the outer solar system have come to be. And I think this could also potentially help us understand exoplanetary systems and Kuiper Belt objects. So that's what I'm interested in right now. I think one of the things that's been really useful in going back to the Uranian system is how science can build on itself, because a lot of what we did for this project is use the original Voyager 2 images as a baseline for understanding the system. And the wealth of work that's been done in the ensuing decades on Umbriel and the other moons, but then also taken into account what's going on at Ceres, where we have much better data and a decent analog for Wunda, and synthesizing those together to try to get a better picture of a world that we haven't seen in many, many years.
Well, for your sake and for all the other people that study icy bodies, I'm going to keep advocating for this Uranus orbiter and probe mission, and I'm really grateful that it's one of the top priorities in the most recent Planetary Science Decadal Survey. But if passes any indication, it might take being up there at the top as a priority a couple times around before we actually get around to it.
It is my hope that we return to Uranus in my lifetime. And that's me trying to set a very reasonable goal. But I think it's one that we can meet if we all work hard. We can get back to Uranus, and it's going to be completely worth the trip.
Absolutely. Well, thanks so much, Adeene, for coming and joining us again to tell us more about these icy bodies. Every time I talk to you, I learn something that totally blows my mind. So I really appreciate it.
Thank you. Thank you so much for having me. There are so many weird little bodies in the outer solar system, and there's just so much to explore.
Thanks, Adeene.
Thank you.
So what I'm getting from this conversation is we really need to send a mission back to Uranus. Umbriel isn't the only mystery out there. The Uranian system is full of moons with wildly different personalities, and we've only seen them up close once during a brief flyby in 1986. And if a seemingly simple moon like Umbriel might have once been geologically active, what does that say about the rest of the system? What about Ariel and Miranda and Titania and Oberon? And this is a total side note, but I think Uranus might have some of the best moon names in the solar system. But names aside, the gravitational dance between these moons could be key to understanding why Umbriel had the conditions for possible cryovolcanism in the first place. So in What's Up, Dr. Bruce Betts, our chief scientist, and I are going to talk about resonant orbits and how they can amplify tidal heating. An orbital resonance happens when two moons settle into a repeated gravitational rhythm. For example, one moon completing 3 orbits for every 5 of another. It's a strange and beautiful thing that happens when the gravitational circumstances are just right. And it turns out it plays a really important role in keeping worlds active when they could have frozen solid. Hey, Bruce.
Hey, Sarah.
Nice to see you in the digital world now instead of the real one. It was really fun being in the office.
I'm much more comfortable with you being in 2 dimensions, and everyone, frankly.
So we did something this week that we haven't done during my time as host of Planetary Radio, which is get really deep into one of the moons of Uranus using data from Voyager. And so it's really interesting to me that they're trying to figure out more about these moons using such little data. I mean, it's just awesome, but also really complex.
Yeah. Planets and moons tend to be that way. And when you have, I've used small data in my life and subpar data, and it does make life more exciting or challenging.
Right.
But that's neat. And the fact, pulling out Umbriel has just never gotten any respect. So that's nice.
Yeah, I tried to insinuate that it was one of the most boring moons in the system, and she's like, actually.
Never insult of scientists, whatever
moon.
They're studying. Pet moon, yeah.
Right. But in the conversation, like we talked a bit about some of the things that could have potentially led to this world maybe having an ancient ocean that's now frozen over. Maybe there's still some water underneath and some cryovolcanism. There's all kinds of interesting stuff that could be going on there. But I realized as we were talking about it, she mentioned that Umbriel could have had a past orbital resonance with Ariel. And then we completely just glossed past it and didn't explain why having an orbital resonance between moons would actually help with the tidal heating. So I wanted to ask you, why is that actually the case?
Yeah, tidal heating is from orbital resonance, which you've got. That's why Io is the most volcanically active moon in the solar system, because it's in an orbital resonance with Europa and Ganymede. And so it goes around 4 times for Ganymede and 2 times for Europa. By doing that, I'll use that as the example. Basically, if you have just your random orbits going along, then big planet, Jupiter, Uranus, whatever big giant planet messing with the little tiny moon, its gravity will eventually circularize the orbit. Basically, it's staying in the same gravitational pull all the time. But if you get another moon that's regularly pulling from the same direction, they basically are lining up with the parent object periodically, and so then they each tug on each other, and they tug each other out of circular. And so when you get into an eccentric orbit, a non-circular orbit, then you're getting more gravitational pull on one part of the orbit than the other part of the orbit. And so what you end up doing is kind of flexing the whole moon at some level. It's like squeezing a rubber ball. If you did that enough, you would put heat into the rubber ball and get a very tired hand. But in this case, the squeezing, so to speak, is coming from the variation in the gravitational pull. And so as a result, you end up flexing, squeezing things, and that it's transferred from that into heat energy, and you basically heat up the interior of this beast, and that's what can cause volcanism on Io or on presumably Enceladus, or if you had it in the past on Umbriel. That's one way, at least the easiest way you can heat the interior to keep things active, because otherwise, particularly a small object, particularly far out in the solar system, but small objects will cool much faster than big planet objects. So your run-of-the-mill circularized moon is going to be chilling hard in the outer solar system and not have any particular new geology going on other than things slamming into it. But if you play the resonance game, you can have all sorts of parties. Now, there's other stuff that's just weird, and they try to figure out these resonances. Like Enceladus has I forgot what the resonance is. It's not nice and small numbers. It's like 17 to 13 with something else.
Some kind of weird fraction.
We've got Pluto with the gravitation. Anyway, you asked me about resonances. We'll stick there. And Pluto does have with Sharon there tidally locked, but that's another story altogether.
Maybe that explains some of the cryovolcanism there too. I mean, I just love the idea of orbital resonance. Just the fact that the universe through physics creates something just that beautiful and weird. That's awesome. Yeah,
it's neat. I've always been particularly intrigued by the 1-2-4 resonance of the Galilean satellites, except Callisto, it's hanging out, ignoring everyone else farther out. But the others are all playing with each other and making things weird.
Interesting too to note that means that like you could have a subsurface ocean on a world and like on a moon that isn't in an orbital resonance, but you'd be way less likely to keep that ocean over time, right? Like eventually you're probably going to cool down because you don't have as much of that. That's one more thing we're going to have to think about in the search for life.
Yeah, I think some people already are at some level. That's why people get excited when they see some kind of evidence of ocean worlds, so to speak, of geysers or other things. And if you want to have a real fun time, try to figure out Triton and why, it's got geysers. What's up with that?
Triton is just weird. I mean, we really
fabulously,
need
wonderfully weird. And it's a bummer that we don't have anything going out there to go play with it.
Exactly. Like the more I learn about all these moons around Uranus and Neptune, it's like the more weird mysteries are out there. I mean, we still have no idea why Uranus is totally on its side. Like we have some hypotheses, right? But the more we sit around not sending missions out there, the more I'm like, we really need to go back. I understand why the decadal survey was like Uranus top priority because yikes, the fact that we haven't been back there in all this time it hurts me inside.
We're lost. We have to go back.
We have to go back.
We have to go back. We'll get there someday. Some humans. Okay. How about a little something different? A little something we do around here called Random Space Fact. Rewind. The mass of the Earth compared to the Sun is like the mass of a mouse compared to an elephant. That was my calculation. I'm proud of that one.
That's a good one.
You have to have kind of a medium-sized mouse and a large elephant, a nice African bull, and it makes it work out. Sun's really big compared to the Earth.
Good way to think about it, Bruce. Thank you.
You're welcome. All right, everybody, go out there, look up the night sky, and think about whether a mouse is more scared of an elephant is more scared of a mouse, or whether you're scared of both. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members. You can join us and help support future missions to Uranus at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme. which is arranged and performed by Peter Schlosser. I'm Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.